Hello, my name is Mohammad Zaidi, and I'm going to present my final project for AI. Let's get started. This presentation is about genetic programming, wisdom of crowds, and the 3 SAT problem. Now, first, we're going to talk about what exactly is NP and NP complete, and what type of problem is this. So NP stands for non-deterministic polynomial time, and it's a type of decision problem that can be verified quickly in polynomial time given a potential solution. Now, NP-complete problems are a subset of NP problems, such as the problem we're going to investigate today, which is 3 SAT. And they're special in the sense that if we can solve any one of them efficiently, we can also solve other problems in NP efficiently. And determining whether a solution is correct for the problem, it might be easy, but finding that solution is believed to be inherently difficult. So 3 SAT problem is a specific type of Boolean satisfiability problem. In simple terms, it involves determining if a Boolean formula can be made true by assigning truth values, true or false, to its variables. So on the left side, you can see one of these formulations in CNF, or conjunctive normal form, where you see we have 3 clauses, and in those clauses, they each have 3 variables, hence 3 SAT, 3 satisfiability. And these variables can either be negated, like you can see with these signs, or they can just be the variable on its own. And then these variables are ORed within the clause, and there's an AND between the clauses. And so the 3 satisfiability problem is seeking to find a configuration for the variables that will satisfy or make all the clauses true. For example, with this configuration. Now, as you can see, x0 is set to false. All of these have not x0, or the negation of x0. So really, no matter what x1 and x2 was, since we have x0 is false, these OR will be evaluated to true, this OR will evaluate to true, this OR will evaluate to true, and so the whole problem is satisfiable. Now, why is 3SAT important? 3SAT is a fundamental NP-complete problem, and many real-world problems or other NP-complete problems are reduced or converted into 3SAT to show that they are also NP-complete and can be solved. And so despite its seemingly straightforward nature, finding a satisfying assignment for those variables can be increasingly complex when the number of variables and the number of clauses grow, as we will continue to investigate. So max 3 SAT, or max 3 satisfiability, is a special formulation of the 3 satisfiability problem. Well, 3SAT is a decision problem. So we have these clauses in the variables, and we want to say, is this satisfiable? Max 3SAT, however, is an optimization problem where we say, okay, is it satisfiable? Yes, but how many clauses are satisfiable? So it's possible that the whole formulation may not be satisfiable, but maybe all but one are satisfiable, or we want to see the maximum number of clauses that can be satisfied, even if that means all of them might not get satisfied. And so a max 3SAT solver would also find the solution for a 3SAT problem if there is one. Okay, so for problem generation, I created a function that creates new 3SAT problems, or 3 satisfiability problems, by taking a number of variables and the number of clauses to generate. And what that does, it returns a tuples with 3 variables. So tuples, like parentheses, and you have the 3 variables that we want, or their negations. So like x, not x1, and x3, for example. And that'll be in a tuple, and we have a list of these tuples. These will represent the clauses, which we know implicitly are the variables are ORed together. And each clause will then be ANDed together. So in order to print this into a nice format for the user, we have another method which would display it in that very manner. So it takes those tuples and it converts the exclamation mark not to this negation not. It converts the commas within the clauses with the OR, and the commas between the clauses with the AND symbol in CNF, as you can see below. Okay, the genetic algorithm. Now we're going to get to discussing how we really went about solving the problem today. We use the genetic algorithm. In genetic programming or evolutionary programming components are these 4. First, you have to have an initial population, and we have to find a way to formulate the initial set of solutions from which we're going to later evolve. Number 2, we need a fitness function, so we need a way to tell how good our solution is. Number 3 is crossover. A crossover is how are we going to allow these solutions to reproduce? We have a fitness function to tell us which ones are good. Well, now that we have good solutions, how can we make sure that these traits get carried forward? That's what crossover is about. And mutation is trying to add genetic variations to potentially push the society forward to escape local optima, and to add more variation as this mimics evolution in real life. So to begin with population initialization, we create a population of just random variable configurations. So we know the variables in the problem, Let's set some of them to true, some of them to false, completely randomly. And this will make the basis for our initial population. That is, for each variable in the three-step problem, we randomly assign it to true or false, like we have below with this dictionary of x0 being mapped to false, x1 being mapped to false, x2, once again, randomly being mapped to false. However, it could have been any random configuration. The fitness evaluation. So for each of the variable configurations, we can calculate how many clauses of the problem are satisfied. So we take these configured variables and we apply it to the problem and we just count how many of the clauses are satisfied. More clauses is more fit, less clauses is less fit. And so we can sort this from most to least clauses satisfied to get a list of our population members or our list of our solutions from best to worst. Now, reproduction and crossover. Now that we have a sorted list of our members from most fit to least fit, we can select two parents from the top range of those members, and those are going to be good candidates to carry their traits forward into the next generation. In order to cross those traits over, we use a random one-point crossover function. And so we select a random index in the middle, anywhere, and so all the variables before that index will get their values or their true or false from parent 1, and the rest will inherit from parent 2. Mutation. And so mutation has several advantages. It adds genetic variety and diversity. It helps search otherwise unreachable areas in the solution space. We overcome local optima, and it mimics natural evolution. So for this experiment, mutation means switching a variable's truth value. So if it's true, we go to false. If it's false, we go to true, and that's a 0.5% chance of happening, because we don't want this rapid mutation. It's something which happens ever so often, because mutation doesn't necessarily add value every single time. Now, if there's sometimes you get lucky and mutation will create a good positive trait, and so that'll get carried on. But if it's not positive, we want that to fizzle out, and so we have a rare percent chance. Now, here is how we went about visualizing it. So you see in the beginning, we have a grid of squares. Each of these squares, in this case 400, represents a clause. And if the clause is false, we get a red square. And if the clause is true, we get a green square. And so we see in the beginning of this loop, we see that there's much more red squares, meaning when the population is totally randomized, in the very beginning, we have plenty of dissatisfied clauses. But we see over time, the number of red squares diminishes and diminishes until we ultimately have a screen which is all green. This means that this indeed was satisfiable, and we have found that satisfying solution. Now, wisdom of crowds suggests that the collective judgment of a group could be more insightful than the judgment of just a single member of the group, even if they're all experts. So wisdom of crowds is based on that assumption, that the individual errors and biases will cancel each other out when we aggregate them across a diverse group. So where do we get that diverse group? We generate a population of expert solutions using the genetic algorithm, which was shown before here. We run this multiple times and get multiple solutions. And then each solution gets to vote on each variable's value. So if the solution said it should be true, false, false, true, false for x0 to 6, and the other one says false, true, true, false, true, well, whatever value they had said is the value they vote for. And we make it weighted so that the most fit genetic solution gets a more say in the vote. And so the way we did that, we did it 10. They get the numbers ceiling of 10 divided by I, where I is their index in the list. So that means the ones who are earlier in the list will get more votes. So the very first position will get 10 votes, and the fifth position will get 5 votes, and the last position will only get 1 vote because of the ceiling. So the best population members get the most number of votes. And we added an extra caveat that if one solution already completely satisfies all clauses, like the one found here, then no aggregation needs to take place. We simply take all the variable values from the original solution, from that one perfect solution. So we generate that population of experts. Each solution gets to vote, and the final aggregate solution is based on the results of those vote. Now we get into our results. So this graph is showing us the execution time. So how long it takes to generate that population of genetic solutions with different numbers of clauses. So we set our variables at a constant 50 and increase the number of clauses. As I can see clearly, it takes more time when we have more clauses to get those genetic solutions, and this is in seconds. However, the aggregation step is a constant near zero time, 0.002 seconds on average, in order to aggregate those solutions with wisdom of crowds. So we see, while it does take longer and longer to generate those genetic solutions, aggregation is a constant time function. And scoring. So scoring we see for the number of clauses from 10 to 550 in increments of 10. We can see the scoring, the best genetic score, the average, the wisdom of crowd score, the improvement based on wisdom of crowds from the best solution, and the improvement from the average solution. So we see in the bottom right corner here, on average, wisdom of crowds was no better than the best genetic solution in the population. That means out of a population of 50 genetic solutions, wisdom of crowds was minus 2.24% from that solution. But on average, so from all those solutions averaged out, and then we do wisdom of crowds, it has a 6% increase from the average solution. So while wisdom of crowds did seem to perform better than the average genetic solution, if you're running multiple genetic algorithms in order to perform wisdom of crowds, you are typically better off just picking the best solution from your genetic algorithm population rather than running the genetic algorithm multiple times in aggregator. And discussion. So the genetic algorithm was effective in finding solutions for 3 satisfiability and max 3 satisfiability, as we can see in the previous video, this GIF. It finds solutions quite rapidly, really. But there's not really an added bonus of the wisdom of crowds every single time. So while we do see in this chart sometimes that the in certain cases the wisdom of crowds isn't necessarily any worse, it is typically not as good as just running the genetic algorithm multiple times and picking the best solution. Now, future research could be done in refeeding the aggregated solutions into the genetic algorithm. So we run the genetic algorithm multiple times, get those solutions, aggregate it, do that multiple times, and then feed them all back into the genetic algorithm and see if we can break through different issues, break through places where we had gotten to a certain number of clauses but couldn't grow past that. Now, part of the reason why we might not have seen such nice results is because our genetic algorithm was already so effective that it was finding good or perfect solutions, and so wisdom of crowds couldn't beat it. And that's why I suggest future research could be done also in maximizing clauses and 3 satisfiability with different ratios of variables to clauses. So here we had set the number of variables constant and varied the number of clauses. But really, if you have, for example, a very high number of clauses and a lower number of variables, you're constrained by those variables. And so there might not be a 3 satisfiability solution. It might not be solvable, but a max 3 satisfiability solution might improve by using the genetic algorithm combined with the wisdom of crowds if we were to do future research into this. Because since it is so restricted with a lower, if it was more restricted with a lower number of variables to clauses ratio, then there would be more ability for the wisdom of crowds to shine. Because in this investigation, oftentimes the genetic algorithm was already finding the best solution. But if there was a bottleneck, there was lower variables to clauses ratio, then the genetic algorithm reached a point where it gets stuck. The wisdom of crowd solution might still become useful in this situation. And so, at least in our study, while wisdom of crowds did not necessarily outperform, it was the best genetic solution of the pool. It was still better than the average solution in the pool. And it only takes a constant time to aggregate, because no matter how many solutions we have in the population, we're only aggregating the top 10 or the top 20% in our case. And so no matter the size of the problem, the aggregation time was constant. And so if we do decide to run multiple genetic algorithms and just pick the best, well, it wouldn't be much more costly to go ahead and run the aggregation and see if we can get a better solution. And these are my references, and thank you very much.